Thank you very much, Martin, for the kind introduction. And thank you all for coming here. I know it's not the best time after lunch, so I prepared a very low-density formulas presentation. Okay? Well, that's the nice thing I wanted to say. The fact is that my background is in biology, so that's what. There are no formulas, but I will try to make it as engaging as possible. Okay? I apologize in advance for the more theoretical people. Don't kill me, please. Well, as it says here, I am Juan Jiménez. I come from the Mathematical Oncology Laboratory in Spain, in the Universidad de Castilla-La Mancha. And my talk is going to be about a discrete mesoscopic model for optimizing temozolomide treatment schedules in glioblastoma. Okay? Well, this is a very, multidisciplinary work in which in silico, in vivo, in vitro data meet together, okay, to come from a problem that we found to propose a new way of treating this tumor, glioblastoma, okay, which I will talk about it later. The talk is going to be a biological introduction first, I'm sorry about that. Then I will talk about the model, okay, the general framework with which I work. Then I will adapt it, I will talk about the parametrization to the special case that we are considering here, the mice experiments that we use to parameterize it, and then finally we will talk a little bit about a virtual clinical trial that I performed with this model. Okay? Well, so first of all, glioblastoma. Some of you may already work with it. Okay? This is a primary brain tumor. Here I put some epidemiology, some incidence data that you can find. Around 24 primary brain tumors. Around 24 people from each 100,000 of them will develop a primary brain tumor, okay, through their lifetime. What's the difference between primary and secondary? Primary is that it's a tumor developed in the brain, right de novo over there, and secondary it's when it comes from a metastasis. Okay, it started somewhere else, but then it migrates to the brain. From all of them, 16% of the PBTs, of the primary brain tumors, are glioblastomas. And glioblastoma is one of the worst tumors you can ever find, of brain tumors, okay? Because it has a very small overall survival, okay? The median overall survival is around 14 months or so with treatment, so you can imagine. It's incurable. The fast progression that I already talked about, it becomes resistant. This is related to the refractory behavior. Like, usually when you treat it, you only have to wait until it recedes, it comes back, okay? And that's the problem about this tumor. That's why it's incurable before, well, in the reduced survival that I was talking about. Biology. This is the pathway the classification has followed across time. I won't enter into the details. I only want to show you that it's very difficult to classify this tumor. Why? Because usually one attends to the genetic description, the markers, everything. So you can see how we started from the Phillips et al. 2006 classification in proliferative, mesenchymal, and proneural. These are different phenotypes. And by the way, now that I say phenotype, if you find any biological word that I say that you want me to clarify or whatever, feel free to interrupt, okay? This was kind of a standard, but it changed through a long time until we arrived to the classification we use today, that for glioblastoma, which was shrink to a shorter classification, we just consider the alteration in IDH, okay? The wild type at the mutant, it's going to define if these tumors live longer or they are short, they have a short progression. Well, the treatment usually relates in two things. Well, for sure, there is surgery, okay? But if surgery doesn't work, if you only can make a biopsy and there is no option to resect the tumor, you can rely on chemotherapy, temozolomide on the left, and radiotherapy, okay? Usually, you give them in a concomitant way, like the two of them together, and then you keep the chemotherapy after. The damage they cause is slightly different because radiotherapy usually creates a faster damage, to say so, and then chemotherapy produces a delayed death. It causes then DNA damage, which the cell has to stop its cycle to take a look and to check if everything is okay and repair as much as it can. So they cell-center into a sort of quiescent state once they when they are affected by temozolomide. But then, if the damage is lethal, the cell is going to die. Okay, apoptosis is triggered, and then everything comes there. Radiotherapy usually is faster than that. But regarding the schedule, the typical schedule for glioblastoma, there is one thing called the Stubb protocol, which is a 1 week on, 3 weeks off, you can see over there, in which during 5 days you apply the treatment, then you wait for 3 weeks, and then for the next week, during 5 days, you keep with the treatment, okay? You may think, okay, we're speaking about a tumor, a very aggressive tumor, there is a very small, the overall survival is very short, but we are hitting it so much with radiotherapy, chemotherapy, surgery. Okay, it looks a little bit like Neo in the Matrix dodging the bullets. Why is that? Well, this may be the perception of people. I want to clarify this a little bit. And sorry for the choice of colors, because I'm noticing now that maybe it wasn't the best. But the point is that this radiotherapy, chemotherapy, temozolomide, usually affect proliferative cells, and not all the cells in the tumor are proliferating at the same time. Okay, there is a marker, Ki67, which is used to determine how many proliferative cells do you find in the tumor. Okay, it's associated to a protein that only appears in proliferative cells, so you can more or less quantify the percentage of cells proliferating. And usually in this kind of tumors, well, you can find a wide variety. Glioblastoma is very aggressive. You can reach up to 30%, 40%, but usually you can find between 5 and 10. Okay. What does this mean? That if you have 5% of proliferative cells, after 1 dose, you may reduce this amount. But the ones not proliferating, the quiescent cells, are going to remain still. Then you keep dosing, you keep administering drug, and you keep killing proliferative cells, but then it comes a point in which, I don't know if you can see the difference between the blue and the purple. Okay, otherwise this is pointless. Well, there is the problem. You see? There's no point in giving more drug when you already have killed all the proliferative cells. In fact, the problem you can find is that there are sometimes types of resistance that are drug-induced. Okay? So, the more exposure, the higher the risk of developing it. So, as you can see, keeping this schedule, probably it's overkill. Okay? So, what's the point? What's the motivation for all of this? What I want is just to find time. Well, what we want, okay? This sounds so strong. The point here is finding time, trying to enlarge as much as we can, not only the overall survival, but delaying the emergence of resistance by looking at different treatment schedules, optimizing them, so as to increase the space between doses, but to keep at least the same survival and trying to hoping for a delayed emergence of resistance. Okay? Well, that's more or less about the biology. Where does this hypothesis come from? Okay, this is not founded on a castle in the air. There are previous works in which they studied this kind of protracted schedules. They are called protracted, okay, for the enlarged spacing between doses, but in low-grade gliomas, which are another type of brain tumors, but they have a much slower development. Like survival can reach up to 10 years, for example, the median survival. This is also a theoretical analysis, but as you can see, they found a difference of almost 4 years in the median between two groups. The group treated with the optimized treatment, in which the doses are enlarged, okay, the spacing between doses, and then the common one, the standard one, the Stubb protocol. So there is motivation to try and find an optimal way to administer this drug in glioblastoma and try to check for an improved way to search for optimized overall survival and delayed resistance. Well, here is what I'm going to talk about, the topic of this workshop, okay? The models with migration, cell migration, interacting particles, here is where they come. We have used a discrete model, the Mesoscopic Model, which is kind of a cellular automaton, stochastic and multi-compartmental, so that a lot of cells can be a single compartment can harbor a lot of cells, which is a little bit different from the typical approaches that you can find in cellular automaton. But the point is that as it is discrete, it allows you to implement biological rules in a very easy way, and then you can find emergent properties from it, which is the interesting point from these kind of approaches. Okay, so now I will go a little bit through the basics. There are a lot of basics, but I will try to make it faster so that you understand the framework. Then I will talk about the case in which we use it to parameterize the glioblastoma. Okay? Well, I won't tell you, I will keep with you. Here you can see a Venn diagram in which I speak about the main paradigms at modeling you have continuous and discrete models, for sure. You cannot forget about biological data if you want to find an application. But what's the problem? Usually, hybrid models, they consume a lot of resources. That's also the problem with discrete models that implement biological data, because they are very hard to scale. Like, you can start with some cells, but you will never reach to the size of a whole tumor, okay? I'm speaking about probably 10 to the 9, 10 to the 10 cells, which is huge for a cell tomato. And then the problem with continuous models and biological data is that it's hard to implement the basics. Okay, like the cellular processes, the scale at which they take place, it's hard to implement over time. Okay? So here is where it appears the mesoscopic model. And what's the rationale behind that? Well, we want to model glioblastoma, so we are considering a 3D mesh, a 3D grid, a space that can harbor a whole tumor. Okay? This has very simple parameters like like the size of the grid and the number of elements per grid. From now on, I will call them voxels because it's a typical name that they use in medical imaging for referring to this kind of compartments, okay? And usually I will select the sizes that allow me to produce the same, to resemble them to the medical imaging data. And inside of each voxel, I will harbor cells. I will have cells like a tumor has, okay? These cells are able to perform basic processes in a stochastic way, okay, like in cerebral automatons, in Markov chains and these kind of things. But what's the point here? Well, the main process that I'm implementing is cell division, and it depends on a probability, okay? I will have a probability of dividing myself every time. You can see the probability over there. I use a delta t, the time step that I take for the discrete model, a tau of reproduction, which is a characteristic time of this process. This is parameterized according to the tumor type that I am modeling. And then there is this term, which is a logistic term, in which A stands for the active cells in that voxel, D are dead cells, and N max is the maximum carrying capacity of the voxel, like a limit set for the amount of cells I can harbor. So what's the point? The probability of division is going to depend implicitly on the occupation. Explicitly, but explicitly it's going to depend on the occupation of the voxel. Implicitly, I'm going to model the fight for resources, the lack of space, the starvation, all of this in just this single term, okay? And why did I put that over there? I can consider like the newborn cells are a random variable, but if I go cell by cell, which is what I want to model here, it will take me forever to compute the updating of every cell, okay? So the mesoscopic model, new point, the new thing that it brings is that instead of considering one single event, which is a cell attempting to divide, which is a Bernoulli process, okay, success or failure, I have a probability associated to each one and it's dichotomic. I can say that picking n cells within the same space and belonging to the same population, behaving in the same way, as a whole set that will let me use a binomial distribution to random sample the number of newborn cells that are going to appear. I don't know if you got that or more or less. But the point is that jumping from n Bernoulli processes, which I'm going to randomly sample at each iteration to know how many cells are going to be born, okay? I jump from there to a binomial distribution, which is going to give me in one step the amount of cells that are going to appear. This is for sure an approximation, and it only works if I consider one voxel, which is a reduced space, if I consider a small time step so that I don't saturate the process, and also if the cells are behaving the same way, which it's granted if they belong to the same clonal population. Okay, we will talk about that later when we introduce the populations over here, but that's the approximation. So that's why I put there, yes, the binomial distribution, because the newborn cells, it's a random variable that follows this binomial distribution. One that depends on AI, which is the number of cells belonging to population I, with that reproduction probability, which depends on the local vicinity inside the voxel. Okay? So this idea is repeated throughout all processes. For cell death, it's the same. But in this case, the probability is slightly modified because I'm not interested in a logistic growth curve. In this case, the more crowded is the voxel, the less resources I have there, the more probable it's for me to die. Okay? So in this case, there is a swap. In that sense, and another important thing is that dead cells remain in the system. I don't wipe them out because usually they are concentrated inside the necrotic core, the center of the tumor, especially for this tumor, which is very aggressive and grows very fast. so there is no way for them to go. Okay, never mind. Inside. Well, there is also some migration. This is a little bit more tricky, but it works more or less in the same way. I divide this process into 2 steps. In the first one, I again randomly sample. I use a probability, randomly sample the number of cells that are going to get out. In this case, my random variable is the number of cells going out of the current voxel. Okay, and as you can see, well, there is a dimensionalization. That's why I put this kind of represent term over there. But it's like the death probability. It depends on the occupation of the voxel. The more occupied I am, the more probable is that I will migrate away. But then there is the problem that I have to distribute all the cells that are going out into the vicinity. And I am considering a Moore neighborhood here, which is made of 26 voxels. So how do I distribute them? Well, I just consider the distance from the center of my voxel to the center of the voxels that I want to go. And there are 3 cases here. The first one is over here, a voxel which shares a face with the central one. The second one is when I share only one side, and then when I share a corner. Okay? So this distance is related to the square root of 1, 2, and 3. Then I use that to create a kernel, which I normalize, and it gives me a set of 26 probabilities, that I plug into a multinomial distribution. So in that sense, the number of cells that are going away, I just distribute them following this distribution in the neighborhood. Okay? Yep.
So when you distribute them, do they move, or do they just make a copy?
No, they move. They disappear from the actual voxel. Yep, that's a good question. Migration and division is not coupled here. Like one process takes place by its own, and then migration takes place independently. Yep, that's it. Well, and then the final process that I want to talk about is the phenotypic transition, which can be regarded as mutation, for example, is the way in which I provide variability in the system. Okay? I talk about phenotypic transitions because it's related to what I'm going to talk after, but the process is very similar. Only in this case, there is again a characteristic time of mutation, okay? But the probability only depends on the number of cells that I have that are able to change its population. Like when I perform a phenotypic transition, I am jumping from one population to a new one, okay? So only the ones belonging to the current population are able to do that step. And again, the same distribution. Well, over time, if we simulate this model, what we have is a very simple algorithm in which we run across time. There are time iterations. I take time steps. At each time step, I iterate across each voxel in the system, in the 3D space. And then across space, at each voxel, I iterate along all the populations that I find within a single voxel. And then for all of them, I perform these processes population-wise, not cell-wise, which is like the thing that lets me simulate a whole tumor, 10 to the 9, 10 to the 10 cell tumor, but infinite time, probably 5-10 minutes, which is feasible. It's affordable for any study that we want to perform. Okay, and in the end, this is just a picture. Okay, I do it myself. It's not the result of the simulation, but in the end, we get to this. We get to a whole tumor. You can pick a section, and you can find the heterogeneity within each voxel inside. Okay. Well, the point is that we have the model.
The different populations correspond to what here? So, what's the difference between them again?
Good question. Here the populations differ in the rate at which they perform the typical processes, like the basic processes. For example, one population may have an advantage at dividing, so it will perform the division process at a faster pace. So it's like a way of simulating mutation and phenotypic transition in the sense that it provides variability in the advantage that they have at performing any basic process.
So, and when a cell undergoes a mutation, it has the same probability to reach any of the other populations?
No, that's the point. We have to define a mutational tree, which is the thing I'm going to do like after some time, after I talk about some more biology, but that's the point. The nice thing to say so is that in this model we can implement any mutational tree that we want, so that we can model any pathway or any tumor that we want, as far as the biology we're implementing it's coherent with the real life. So yeah, I didn't explain anything about that because I will go on that later, but that's it.
Thank you.
Well, speaking about that, I'm going to put you just 3 examples in which the model participated, which are kind of validation for it. Because so far I spoke about a model, and well, that's fine, but it's a discrete model, it's not continuous, there is no formal description of it. You may think, okay, this is nonsense. Well, for the first study, we parameterized it also for glioblastoma, but in this case, we didn't use any treatment. We just wanted to reproduce as far as we could a real glioblastoma in terms of overall survival of untreated glioblastomas, okay, because there is no treatment here, volumetric measures, and heterogeneity also, because it's a highly heterogeneous tumor in the sense of different populations. So we plug a mutational tree based on the most predominant altered pathways in this tumor. Well, it's a enter over there. The point is that with this simple model, we were able to reproduce a feature of this kind of tumors. I don't know if I can. Yeah, over there. You can see a tumor here. You can see this kind of white ring around, okay, which is the contrast enhancing area. This is associated to a more proliferative area around the tumor. The point is that we are able to reproduce it in the model. And why? Because usually the most aggressive populations, the ones that proliferate faster or migrate faster, are going to crowd more the boundary because they will be more abundant there, like before what Tommaso talked about. So usually when you find them over there, there is this contrast enhancing ring, which is more populated, more crowded with these cells, and as they grow more, they are going to produce a higher signal, which is the thing that appears over there in the magnetic resonance image and is reproduced over here in the distribution, in the heterogeneity, how it's distributed across space on the model. Okay, so this was just an example. You can take a look if you want to check the volumetric and everything, but I can tell you that the parameters of division, migration, everything was validated over here. Then in this work, we use it to parameterize lung and breast cancer, and it led to a very beautiful, in my opinion for sure, but a study in which we found a new biomarker, which is called NHOC, which is the normalized distance from the hotspot of activity to the tumor centroid, and it's a measure which only tells you how far from the center is the point of maximum activity, relating this to the contrast enhancing ring. The point is that the more far away you are from the center, the more aggressive this tumor is going to be. Okay? So in this case, we used the model to parameterize a different tumor and it worked well again. And finally, in this study, we didn't parameterize any tumor, not a specific tumor, okay, but in general. And the point was to, the topic of the paper talks about a universal scaling law for tumor growth in which they find that the exponent of, it's not here. Like this, there is a board over here. Well, maybe you are familiar with the Clever law, which is a scaling law that relates the mass and the metabolism of organisms. Okay, he found an exponent is something like that, as far as I remember. Mass with the metabolic intake. Okay, it's a sublinear exponent. That means that if I grow more, I need less resources to keep that metabolic rhythm. Okay, the point is that a similar law was discovered for these for tumors, for aggressive tumors, and in that case, this exponent was close to 5-fold, which is superlinear, meaning that the more that I grow, the more resources I need to keep this rhythm. Okay, so the model participated here as a test bench for proposing a hypothesis, and the hypothesis was that the clonal competition, the competition between different populations, was the underlying mechanism giving rise to this exponent. In what sense? Okay, we just simulated a plain tumor, a tumor made of one population which behaves in the same way, and then we simulated tumors with a different mutational tree. Like there is heterogeneity, some new populations can appear, and these populations will behave in a different way, usually more aggressively than the previous one. So what we found is that the homogeneous tumor had a less than one exponent, okay, a sublinear one, but the heterogeneous tumor that we simulated had a higher than one exponent, meaning that the superlinear behavior, the explosive growth, depends on this competition between clones. Okay? This is just for validation. Now we'll go back to glioblastoma. And now that we spoke about biology, now that we spoke about the model, okay, we have to parameterize the model. But before, we have, as Tommaso said, we have to implement the basic biology that we want to plug into the model, into the events, into the rules, okay, so that we can reproduce a realistic tumor. Well, here is where we try to implement two things that so far haven't been considered in the resistant, in the emergence of resistance or in treatment in general, which are the persistent dynamics and the proneural to mesenchymal transition. I will go through them very fast. They are easy as far as they go, okay? But the first one is that in this work, they found that the persistent paradigm, which is becoming more and more famous now, it says that resistance comes through an intermediate state, which is called persistent, and it's the drug-induced state, which cells can enter after exposure to drug, and then they can remain there, but if drug is removed, they will go back to the initial state, their drug-sensitive state, okay? But if drug is, if the exposure is prolonged, then they will enter a fully resistant state, a non-reversible one, okay? Which is the difference. In this work, they found that persisters were present in glioblastoma, okay? So, we want to implement these dynamics in the model. This is going to be one part of the mutational tree that I was talking before, of the phenotypic transitions that can take place. We can start at a temozolomide sensitive place, then after drug exposure, after temozolomide exposure, we can go to persister. If temozolomide is removed from the system, then we can go back. But if it's prolonged, then we can enter a fully resistant state. This is one of them. And the other one is the proneural mesenchymal phenotypic transition, which is also observed in glioblastoma, as this work says, and it's associated not only to treatment, as it says the figure, but also to a spontaneous process, in which the tumor, a tumor which starts mainly as proneural, can evolve, can progress to a mesenchymal state. Okay? This is important, and this is also the thing that we are going to introduce in the model. So, here we have the ingredients, here we have the cell populations that we are considering, the proneurals and the mesenchymals, in the middle the persisters. And for all of them, we are considering two states, the sensitive one, the proliferative one, which is going to be the one that can be affected by the drug, like in the first case that we talked about, and then the quiescent one, which is the one not proliferating, the one that drug is not going to affect, but it's going to remain still. Okay? And what are the transitions that we model? First of all, sensitive cells proliferate, either proneural or mesenchymal, all of them. Then sensitive cells can become quiescent with a proper rate, which is defined over there. We will talk about that later. But this process is reversible. Okay? So like quiescent cells, they can gain back proliferativity after. Then temozolomide can kill sensitive cells, but temozolomide can also trigger this transition to persistent state. Okay? Then this state is an intermediate reversible state. If we remove temozolomide, we go back, and then if we keep the treatment, we enter the mesenchymal state. Notice that we enter into the mesenchymal proliferative state. Okay? Because mesenchymals are going to behave in the same way as proneurals, except for the rate at which they perform the basic processes as we were talking before. Okay? The Quiescent Dynamics we have here, that's it. So this is the whole picture. Well, what I forgot to say is that the proneural mesenchymal transition is modeled like this long arrow from the left to the right, which spontaneously it's going to trigger the phenotypic change. And what is what triggers this change? The microenvironmental conditions. If I am within a voxel and the voxel is getting very crowded, there is a chance that I can get over there directly. Okay? Well, this is a picture of the model. We have how it works. We have the biology. Now we have to find the parameters to reproduce it. And I can tell you, finding the parameters is more or less like that. You have to fish, not in the bad sense, like, okay, pick the one that I want. It's not that. I mean, you have to fish because you have to swim across the literature to find the biology, to find the proper parameters, and so. But there are some parameters that nobody tells you what is the value, or there is no way to measure them. Okay, and some of them are the rates which lets you go from quiescent to sensitive to proliferative and forth. I will tell about that later. But The good point, the nice point, is that the biology enters here. We had some collaborators in Madrid that they were working with mice, and they had developed 2 different models for glioblastoma in mouse. Okay, but they were a slow-growing model, which is more related to slower glioblastomas, the IDH thing classification that I talked before, and then another one which is fast, which progresses much faster. What are the characteristics? The first one, the slow one, has a 10% of proliferative cells. The fast one has a 30%, which is much more. And then you can see that in the OS, the overall survival, which is from 25 to 32 days. Okay, these are the names over there, but I don't mind. The fast-growing tumors, the fast-growing model, and the slow-growing model. This is the process. This is the procedure that they follow, and that's the one I will use to parameterize the model. I will tell you later why. They start with an inoculum, this amount of cells, then they treat, well, following this schedule, and then usually the mice dies when the tumor volume reaches 20 millimeters. That I can use in the model because if I let the system evolve until it reaches this amount of cells, then I can consider that from this point to the point in which I feel 20 cubic millimeters, then I can say this is my overall survival for the mice. So in that, yeah.
Do you know what the phenotypic traits of these initial cells are?
What, sorry?
Do you know the phenotypic traits of these initial cells are?
The distribution, they come from they are a primary cell line, but I cannot tell you. I guess it's an equilibrium mix of cells from a typical tumor. Okay. So the point here is that this data I can plug in a model to calculate an overall survival in simulations. Okay. So that I can use it to parameterize the model. In which way? Finding the proper mu QS and mu SQ, the parameters that let me go to a quiescent state and back, and trying different values for them, for different combinations. I can find those producing the overall survival that I want at the left, and the percentage of proliferative cells that I want at the right. Okay, so I just have to find, well, these are results from simulations. This is an interpolation that I made to find more grid points in the parameter space, and for all of them, well, there seems a few. Repeated this several times, but I'm putting this this image. We found the points at which we can reproduce fast-growing tumors and slow-growing tumors. Okay, if you check, you have the survival over there and the percentage of proliferative cells. Well, it's close to 35 over there, and it's very reduced. It's close to 30-35 days. And then we have the slow-growing ones, which reach more than 60 days, and then they are around 15, more or less, 15% of KH67. And then you have the parameters over here giving rise to them. Well, there are not so much in here, as I say, but it's a way to provide an estimate. It's kind of a Bayesian inference system to get values for these parameters, so that we can already simulate mice, okay, based on this data. There are more parameters for sure. The parameters related to migration and everything, they were previously fit in the works that I talk about. And then the parameters about therapy, how do these cells react to therapy, they were taken from literature, okay, from the previous papers that I talked about. And, well, once we have this, now we get at the point at which experiments are going to take place, in which they are going to analyze the mice, and at the same time, we are going to simulate mice tumors, tumors parameterized for mice, following the same schedules. If you recall, I will tell now, we were looking for protracted schemes with a longer spacing between doses that can let us get a better overall survival or a delayed resistance. So what we tried, a standard therapy, which is the one over there. We applied 3 doses, with the first dose starting 7 days after the initial inoculum, and the spacing between doses was 1 day, which is kind of an intensive therapy. Maybe not, well, it's hard to scale from mice to humans, so probably it's not the same equivalence, but it is related to the typical way in which temozolomide is administered in humans. And then progressively increasing those spacings, okay? And first of all, for the simulations, here I flag just one simulation, one result. At the left, you can see how the preneural to mesenchymal transition takes place. You can see how the percentage of mesenchymal cells increases over time. There is a rendering of the 3D tumor, and in the different colors over there and here in different sections, this is a middle section, you can see the preneural and the mesenchymal distribution. As you can see, at the last point, the mesenchymal mostly covers the whole tumor, it's around 60% or so. Okay? And then taking a look at the data, we have on the left the fast-growing tumors, and on the right the slow-growing ones. And at the top, the difference in survival between a controlled state in which mice are not treated, simulated mice, and then we apply the different schedules, and down below we have the percentage of mesenchymal cells, which mesenchymal are assumed to be more resistant. I think this is something that I didn't tell you before, and it's important, sorry about that. Mesenchymal cells are more resistant than the proneural cells, okay? So what we can see, if we attend to the fast-growing tumors, we can see that there is a difference in survival. It's very small, for sure. Also, the overall survival of the mice is small, but well, we see it. Another important thing here is that all the simulations that were performed, I use a different random generating number seed for simulations in the same branch, to say so, for example, in a one-day spacing, but I repeated the same random generation seed across the different branches, so that in that way we can isolate the effect only to the treatment, not to any stochastic effect, okay? So this is a paired non-parametric test, the one that I performed here. The important thing is that for survival, we can see there is a significant difference against the control for all of the cases. An interesting thing is that for the mesenchymal content, for the increase in mesenchymal content compared to the control, for the fast-growing tumors, we see a very high increase, okay? We can get up to 50% increase in resistant cells. But if you can see, for the slow growth, there is a small percentage of them which reduce the mesenchymal content, not so much, for sure, but it coincides with the longer spacing. So, from these in silico results, from the simulation results, we can say that we should expect an improvement, okay, for the because of the spacing, and also a reduction in the mesenchymal content. Now, here it comes, the results in mice. Down below, we have the model, which grows fast. You can see that for the, well, it's very small, but the short overall survival. And then up there, we have the slow growing tumors. What you can see is that these schedules don't work for the fast growing ones. For example, you lack the last one, the 13-day spacing, because the overall survival was so short that there was no way of applying it, okay? So they discarded this data. But for the slow growing tumor, we found that effectively there is a difference in the median survival between groups, and it's significant for the 7-day spacing and the 13-day spacing. So there is an evidence in mice, in vivo for sure, so this doesn't mean that in humans it's going to work, but there is a difference predicted by a discrete model which turned out to be real in vivo, about this supporting the application of these schedules. Okay. This more data. This is the expression chart for resistant genes. Okay, you can find over there MGMT. This is very famous because it's related to glioblastoma progression. It's related to the resistance to temozolomide. Okay, and you have three different bars. The control one in red. The orange-brown one for the 4-day spacing, which is kind of an intense spacing also, and in red, the one for the 13-day. I'm sorry, I thought I saw a hand over there. The red one for the 13-day spacing. And what's the point over here? As you can see, the expression increases a lot when the spacing is short for the 4-day one, but it keeps the same level as in control, or even reduces for the 13-day schedule. What means that in mice, again, we reduce the mesenchymal content, which is also related to resistance, okay? And finally, this is a different way to take a look at the same thing. Here we have proneural markers, the expression of proneural markers, and of mesenchymal markers, which can be considered the resistant ones. And what we can see is, again, that the longest spacing increases the proportion of proneural cells and reduces the mesenchymal content, okay? So it's a nice way to validate a model for sure. I mean, this is what not always happens, but when it happens, it's nice for the modeler. Well, but we didn't stop here. We said, okay, we have a proof in real life, but we want to make a real change. We want to provide of some way to implement these results in the real life, in the clinics. And what did we do? We conducted a virtual clinical trial. Okay. We parameterize the model again, but for humans this time, which is just a matter of escalating again things, and we run different simulations considering different treatment schedules Okay, just to check what happens. And if in this way we can provide an estimation of what is the best schedule that we can find. Again, we have to fish for parameters. We perform the same analysis as before. In this case, only for the parameters balancing the proliferative and quiescent content, because in the end, it's the most important one. It's the one that is going to give you not only the Ki-67, the proliferative percentage of cells, but also the survival. Okay, and we found in this time the interpolation was finer, the grid I mean, a much bigger set of parameters that will let us simulate fast-growing glioblastomas and slow-growing glioblastomas. If you go back to the classification that I showed before, these are related also to the mutations in IDH. Okay, so in this way we have like the resemblance with the mice but applied to human. For sure, this is in silico, this is a prediction, but in any case, we have it here. And well, you can see over there the overall survival. Maybe you can notice this is short, but take into account that again, this is for control. Here we are not applying treatment yet, so far. Here's the schedule that we follow. We consider a lot of ways of applying the doses, but we also thought that usually clinicians, are not so eager to change their procedures. Like if they have a standard, they're going to stick to it, even though there is no rationale supporting it. I'm not saying that here, but this rationale supports a protracted schedule, so we have to combine them. What did we do here? First of all, we tried the standard one, which is also a way to parameterize the model, because if we get a similar difference in the median survival between control and the standard group, okay, we can say that we are working fine with the model. And then we tried two different things. First of all, to increase the time between cycles, because remember, we are giving 5-day cycles separated by a resting period. We increase this resting period from 3 weeks to 9 weeks, and then we play with a different way of applying drug, which we call LDD, lower dense dose regimens. Okay, in which what we do is to increase the spacing between doses without resting periods. We just increase the time in which we apply the doses. And we choose an 8-day one and a 12-day one because they are significantly higher than the usual ones applied. And for the fast-growing tumors, we observe this. As you can see in the treatment, the median gain is around 2 months. This is consistent, more or less, with the available data. But as you can see for the protracted one, the one with the 9-week resting period, we didn't observe any improvement in survival. But for the one with the lower dense regime, in this case the first one, the one with 8 days between doses, because the other one was impossible to apply in the same way as with the mice, we see that the survival is kept, well, it increased a little bit, but there seems to be a branch of long survivors greater than the other one. I have to say that there are 15 patients per branch in this case, and the parameters are randomly sampled from the ranges that we obtained before. So in this way there is some variability so that we can perform this Kaplan-Meier analysis, which, by the way, the cumulative survival fraction is the fraction, the percentage of patients that are alive as time goes by. Okay, so I think it's more or less straightforward to understand this graph, but if you have any doubt or whatever, you can tell me. Well, I'm telling you this after several Kaplan-Meier graphs, but anyway. And I'm sorry for the letters over there. This is not a go, this is just because they come from the figure that I prepared and I have to mix them a little bit. But now we are observing the slow-growing ones, and in this case, we have more room for trying things. And what did we try? First of all, the standard over there at the top corner at the left, which again, we observe a coherent difference in the median survival between control and the treated group. And then we tried the protracted scheme. We seem to improve a little bit the overall survival, but this may be an artifact just because of the median placement. But even though we observe again this branch of long survivors, but then we try the different low dense dose regimes in 3 different modalities, with 6 cycles, like keeping the same dose as we give in the standard one, doubling this amount of dose, like giving 12 cycles and then giving 18 cycles at the bottom, okay? And what you can observe is that the improvement is huge, okay? You can see from 6.7 months to 7.1, well, not as much as in the one at the top right, but in any case, this supports the idea that increasing the spacing between doses, it's better for the patient. Here I don't have the data for the resistance, okay? But in any case, just increasing the survival supports the idea of applying. So, the main conclusions, I think, yeah, perfect. The main conclusions can be, first of all, that the mice experiments confirm the prediction from the mesoscopic model, from the discrete, the in silico results, in terms not only of overall survival, but in terms of resistance and toxicity. This is something that I didn't put here because it was way more biological than that, but they also observed that the amount of blood cells remaining in the mice after the whole treatment was it wasn't lost after chemotherapy in the ones with the longest spacing. So again, this is another proof supporting these schedules. Then in silico results suggest that for fast-growing tumors, there could be a benefit if we apply the low dense dose regime, and then for the slow-growing tumors, we can do whatever we want. The model supports that increasing the spacing is going to be beneficial for them. Okay. Well, this is a work that was made in collaboration with a lot of people. There is the modelers that we work at Mathematical Oncology Laboratory, but there is also the people working with the mice at Instituto de Salud Carlos III, people from Serbia working also with in vitro cell lines of glioblastoma, and a whole lot of financial stuff and everything. Okay, that's it.